So I grew up in a house wrapped around a 300-year-old oak tree. And maybe that's where my fascination with how we adapt to our ever-changing physical environment started. As a kid, I learned to live in constant balance with nature, as it was quite literally part of our home. It wasn't something to control, but respond to. In winter, we watched for weak branches that could break under the pressure of heavy snow and crash through our roof. In spring and summer, we monitored fellow residents of our oak tree, like squirrels, chipmunks, and carpenter ants, who wrought havoc on our home as they went about making theirs. And in autumn, we spent hours raking the leaves that buried our house under a golden layer of fallen foliage. Going through my childhood art box shows how intimately the natural world was a part of my life. I felt like we lived with it. Didn't all homes sit perched in trees? Or even better, from a drawing that my sister did, weren't all homes basically trees? I grew up with a unique perspective on how impermanent and alive the Earth is, and how constant change, even on geologic timescales, influences our daily lives. The Earth is dynamic. Everything from windstorms to ocean waves is directly linked with the predictable rhythms of the Earth's constant motion. Motion, it turns out, that started back in the early days of the galaxy, before the Earth had even formed. To start our journey into physical geography, we're going to go back to the beginning of everything. I'm Alize Carrere, and this is Crash Course Geography. Geography is all about appreciating the big picture to reveal the geographic patterns and processes that create Earth's environments and support all living things. So in the big picture, about 13.7 billion years ago, the universe began. We could talk about the physics of that for a whole episode, and we have. But to get to the story of the Earth, we need to zoom into the Milky Way galaxy. In one remote arm of one of 125 billion galaxies, about 4.5 billion years ago, a swirling cloud of gas and dust, called a solar nebula, collapsed under its own gravity. It spun faster and faster and flattened into a disk. Almost all of the nebula's material was sucked into the center, forming the sun, but a tiny fraction of a percentage spun out. And that's what formed the rest of the solar system, including the Earth. We can still see the effects of this dramatic event in how the Earth and the rest of the planets and asteroids move throughout our solar system. Our whirling and twirling days aren't behind us. The Earth spins, or rotates, on an imaginary axis that runs from the North Pole through the center of the planet to the South Pole. It takes the Earth just under 24 hours, or one day, to spin once on its axis. At the equator, the Earth is actually spinning at about 1,600 kilometers per hour, which to my brain at least, basically sounds like very fast. But to really get a feel for what's happening, let's use a reference point. A cheetah, one of the fastest animals on Earth. A cheetah can put on a burst of speed of up to 120 kilometers per hour to bring down that impala it's chasing. No, not the antelope. They could catch those for sure, but I'm talking the car, on a freeway. The rotation of the Earth at the equator is still 13 times faster than the top speeds of a cheetah. At the equator, we're moving the fastest because we have to rotate the entire circumference of the Earth to get back to where we started. But if we're anywhere else, we move in a much smaller circle. So if we're in St. Petersburg at 60 degrees north latitude, our speed would be about only half that at the equator, 830 kilometers per hour, or about 7 times faster than our cheetah. And at either pole, it's the speed of a cheetah napping. So every day, while we're brushing our teeth or standing in line for bananas or even sleeping, we're moving faster than a cheetah ever dreamed possible. Well, as long as you don't live near the North or South poles. Everything in person on Earth, including the atmosphere, is rotating with us, which is why we don't recognize that we're spinning. We don't have any nearby moving objects we can compare Earth's movement to. While stuck on the surface, we can get some limited help from the main object in our sky, the sun. It appears to move because the Earth is rotating, which changes our view of the sun over the course of the day. If we were floating above the North Pole, Earth would be rotating counterclockwise. That gives the impression of the sun rising in the east, moving across the sky as it climbs, and then setting in the west. And then if we look at the Earth from a distance, like astronauts on the moon, we'd actually be able to see the Earth rotating because we wouldn't be rotating with it anymore. In fact, we'd even be able to see the gradual movement of the circle of illumination, which is the dividing line that separates the half of Earth that's currently receiving light and solar energy from the other half that's in total darkness. Though we'd have to watch pretty carefully to notice the Earth doesn't spin perfectly. Let's go to the thought bubble. The Earth, it turns out, doesn't spin like a perfect top. It wobbles ever so slightly. Some of the Earth's wobbling is actually predictable, like a spinning top slowing down. The Earth's axis wobbles on a 26,000-year cycle known as precession that changes how the Earth's hemispheres are oriented towards the sun. So the North Star, or the star almost directly above the North Pole, cycles through several stars over time. Precession is one of the Milankovitch cycles, named after the mathematician who deduced them in the 1940s. Milankovitch cycles influence Earth's climate by changing how much solar energy reaches the Earth. But in 2000, the wobble took an unexpected and relatively rapid turn east. So with the help of the GRACE satellites launched by NASA and the German Aerospace Center to record data on anomalies in Earth's gravity field, Scientists looked for answers in the Earth's mass. They found that melting ice from Antarctica and Greenland are causing sea level rise, which affects land masses too, pushing and pulling the Earth as it rotates. But human water use in Eurasia is having an effect too. Groundwater beneath the surface is being used faster than the hydrosphere can naturally replace it all over the world. But as we get closer to 45 degrees north or south latitude, small changes have a big impact. Coefficients in the equations that best describe the Earth's wobbling depend on latitude, and the coefficients are biggest near 45 degrees north or south latitude. So any changes in mass that happened around there are amplified. NASA estimates dry years cause the Earth to wobble east, while in wet years, Earth wobbles west. That's right, how we use and store water can steer Earth, or at least wobble it a couple of centimeters. Thanks, Thought Bubble. Now, the Earth isn't just wobbling around arbitrarily in space. The Earth travels on a 940 million kilometer path around the sun, called an orbit. One complete orbit is a revolution, which takes 365.25 days, which doesn't fit nicely into a calendar. So to make up for the extra time, humans decided to add a day to the calendar every 4 years. Happy Leap Day? Earth's orbit is actually elliptical, like a slightly stretched out circle. This means that the distance between the Earth and the sun varies a bit throughout the year. Specifically, the Earth is nearest the sun, or at perihelion, in January. And the Earth is almost 5 million kilometers farther away from the sun at aphelion in early July. Our varying distance from the sun isn't really linked to the daily weather here on Earth. We'd only see big changes if we were to jump into the orbit of like Mercury or Saturn. All the planets in our solar system rotate and revolve around the sun on elliptical orbits, though on dramatically different time frames. Because of how the solar system formed from that swirling disk we talked about, most planets orbit on or close to the plane of the ecliptic, the imaginary plane that contains Earth's orbit. The Earth actually tilts 23.5 degrees away from a line perpendicular to the plane of the ecliptic, which probably happened after some other space object knocked into it billions of years ago. All of these movements, along with the shape of the Earth, influence the amount of sunshine each part of the planet receives, which sets in motion the processes for those windstorms and ocean currents and even weather, all of which influence where we grow certain foods and what we need to build shelter. In geography, to be more specific when we're talking about the movement of energy, we call sunshine insolation, which stands for incoming solar radiation. It's what drives the different Earth systems, like we talked about last episode. Because the Earth is a slightly pudgy sphere, insolation doesn't end up being equal everywhere. Only one latitude will receive the most intense and concentrated direct rays. The rest receive slanting rays that have to pass through more atmosphere, which bounces the light around and spreads it out. So we've got Earth rotating on a tilted axis, pointing in a particular direction on an elliptical orbit with solar energy hitting the surface at different angles. Sounds like a recipe for something. Definitely not disaster. More like the recipe for life on Earth. How much sunlight we receive is responsible for everything from how much food we're able to grow to how much water moves around the planet, and whether we have to wear a heavy coat when we go outside. In other words, how the Earth moves changes the seasons. The best way to understand the progression of seasons is by following the Earth around its orbit and looking at the insolation. On December 21st, or the December solstice, the South Pole is tilted toward the sun. Everything south of 66.5 degrees south latitude in the Antarctic Circle receives 24 hours of daylight. And at noon, the sun's rays will be directly overhead the Tropic of Capricorn, or the latitude line marking 23.5 degrees south. This is the strongest insolation the southern hemisphere receives, and it's the peak of summer. But the tilt of the Earth means that on the December solstice, the North Pole is tilted away from the sun. Everything north of 66.5 degrees north latitude in the Arctic Circle experiences a full 24 hours of darkness. With weak insolation, the northern hemisphere is in winter. As the Earth continues along its orbit, the sun's angle and the day length gradually increase in the northern hemisphere. Near March 21st, or the March equinox, the Earth's axis isn't tilted toward or away from the sun. And the circle of illumination, that line between day and night we can see from space, passes through both poles, bringing all locations on Earth equal hours of day and night. Spring has arrived in the northern hemisphere, and this is the first official day of fall in the southern hemisphere. Then we have the June solstice, around June 21st, and the exact opposite conditions from the December solstice. The North Pole is tilted toward the sun, while the South Pole is tilted away. At noon, the sun shines directly over the Tropic of Cancer, the latitude line marking 23.5 degrees north. The Tropic of Cancer and the Tropic of Capricorn mark the boundaries on the Earth where the sun can shine directly overhead. At either pole, the sun will never be directly overhead. And finally, we reach the September equinox around September 21st. Once again, the Earth's axis isn't tilted toward or away from the sun, so the poles have equal hours of night and day. Only this time, it's fall in the northern hemisphere and spring in the southern hemisphere. The seasons, and all they mean for how we've adapted, are only possible because of processes literally set in motion before the Earth even existed. If the Earth didn't rotate, half the planet would be an ice dungeon and half would be on fire. If the Earth didn't revolve, the length of a day would remain fixed yet drastically unequal around the world. Our life decisions are influenced greatly by the motion of the Earth. It guides where we decide to live, what food we eat, or even what weather we experience, which we'll start talking about more next week.